In this lesson I'm going to show you how to split B-spline curves with OpenCascade API functions. For that I'm going to load an IGES file containing a curve network, and I'll start with declaring a function to read an IGES file. It's just a global function here in this example. It accepts a file name as an ASCII string and it returns the loaded shape. Here I have the IGES control reader class that would bring me the pure geometry without any metadata such as colors and names. If you want to read some colors and names and any other metadata, you might want to consider using IGES CAF control reader. Then I read the file. As usual, this get file translation is a two-stage process. So the first thing to do is to read the file itself, and here I obtain in-memory representation of my IGES entities. And after that, if everything is fine, if my file exists and it has like valid structure, then I can proceed with transfer routes, and here actually all those in-memory data structures will be turned into TopoDS shapes, into real geometric primitives. And then I take all the translated entities as one shape and store it in the result variable, and then it is returned. So let me try to run this function right from the main function of my exercise. And I also have to declare a shape. And if something goes wrong, then I simply return an error code. In the case of success, I can just output my shape into my visual stream as we usually do. Now let me run my main function, and you see that, okay, here I have a curve network, and this network represents something very similar to a turbine blade. And if I hover my mouse cursor over those curves, I see that all those curves are complete curves. And what I want to do now is I want to intersect them explicitly so that I get explicit representation and coordinates of their intersection points. This can be helpful if, for example, I want to reconstruct this surface out from this curve network. One solution would be to try to build Kunz patches for each cell and then to concatenate them smoothly to each other. So let's go ahead and try to find intersections of those curves. For that I'm going to use one variation of Boolean operations provided with OpenCascade library. So let me just copy and paste this Boolean general fuse function. So basically there is such an operator called general fuse in OpenCascade, and in order to use it you are supposed to have this BOP algo builder, which is essentially this Boolean operation engine. So let me just go ahead and include it. What this function does, it accepts a list of arguments, all the shapes that I want to intersect with each other. Then it accepts like a tolerance, because Boolean operations, they use the tolerances as they are defined in the input shapes. And if I want to modify it, if I want to give them some explicit tolerance to use, then I can do this with what is called a fuzzy value. This BOP algo builder class, which is essentially Boolean operation itself, is passed as an argument, simply because I want to access the history of modification later on. If that was not the case, then I could have probably encapsulated the use of this BOP algo builder right within the scope of this function. Then, how it works, I first have to declare what is called a pay filler. This class is responsible to finding all so-called interferences between the arguments, which essentially means that this is the finder of all intersections. This tool is going to intersect all topological entities with each other, starting with vertex to vertex intersection and then increasing the dimension, like vertex to edge to edge, edge to face, and so on and so forth. So let me go ahead and include this pay filler so that I can use it. Then there is an argument if I want to run my Boolean operation in parallel mode. I'm going to turn this parallelism mode off because I'm not sure if it's helpful or not, but you might want to experiment with this flag here. Then the fuzzy value, this is how I explicitly pass the tolerance, so that preventing Booleans from using the tolerances as they are defined in the input shapes. And then I ask filler to perform, so that I ask for all intersections to be found. Then I check OK if there are any errors so that the Boolean operation cannot proceed, and if it's like that, then I just return an empty shape here. There is a dedicated mode for gluing, but let's not discuss it right now. And what we will discuss is how we run the Boolean operation. We simply pass the arguments into this BOP algo builder. We said, okay, we are not going to do any parallel processing once again, just like we did here, and then we pass there our pay filler. We pass our pay filler with all the interferences found to the Boolean operation. And then the same story, we check if there are any errors upon the completion of this Boolean operation, and if yes, we return a null shape. If not, then we return the result of the Boolean operation. So let's probably get rid of this gluing mode, just to simplify this whole business a little bit. And now we are supposed to compose the input arguments for our Boolean operation. So we have our shape, and what we are going to do, we are going to explode the shape onto the individual edges. For that, I'm going just to run an iterator, and in this particular case I can use TopExp Explorer, iterating my shape by all the edges. So here I put a qualifier saying that I want to obtain all the edges contained in my shape. And if you say, okay, this is something weird, we can probably just go ahead and include this TopExp Explorer as well. This more function would check if there is anything else remaining to iterate, and then we move the iterator to the next position. And I'm going to compose TopTools list of shape. This collection is pretty similar to std vector, except for the fact that here the indexation starts from 1 and not from 0. So now I can just append the currently iterated edge to my collection of arguments. I do that using Explorer's current method. There we go. So now upon completion of this procedure, upon completion of this loop, I have all the arguments, all the edges that I want to intersect with each other. What is important to notice here is that those shapes, they should really be like topological shapes and not curves. If you have plain curves like geom_curve handled, then you first have to turn them into edges. But fortunately this is already done by IGES reader, so I do not really care. And what I care of is to create this BOP algo builder, like a Boolean operation, and then I can run my fuse operator, passing there these arguments. Then I have to decide on the fuzzy value, because actually I'm not sure that my curves are intersecting very precisely, so probably it would be sufficient to set something like this, and then Boolean operation. And if my Boolean operation returns null shape, then I simply return an error code. Well, basically here I have to take out my result, because I also want to visualize it on the display. And now, instead of using this vout.sh, I am going to visualize my result like this. So I do not pay attention to those warnings. They have something to do with, iterators of OpenCascade. Basically, what you want to do with those warnings is to simply suppress them. Alright, you see that upon completion of my Boolean operation, now I have all those curves split, and I have individual edges. So basically I have all the vertices. It would also be quite easy to extract explicit vertices out of this result, so for that I'm going to use TopExp exploration tool, then map shapes. Here I would pass my result, and I would say that I would need all the vertices. And please put all those vertices into TopTools indexed map of shape, which is basically just a set of shapes. Now if I want to visualize them, I can probably create a compound, just in order to have all those vertices as a TopoDS shape. So I would declare a compound. Then I'll create an instance of BREP-builder. This is a tool that you normally use to build all topological entities explicitly. This is used everywhere in OpenCascade. IGES. And the first thing to do using this B-builder is to make a compound, so that to allocate all required resources, like to allocate dynamic memory and prepare this compound for being populated. And after that I can iterate over my vertices starting from 1, then extend. And here what I do is I use the same builder, then add. The first argument would be my compound, and then I add a shape. So basically here I have to pass this next vertex, and I can do it as simple as that. Upon completion of this iteration, I have this compound populated with all the vertices, so then I can just see out them like this. Let's see what's going to happen. You see that now I have all my vertices evaluated explicitly. So now that we have all those curves split and we have those vertices as 3D points, you might ask, okay, why would we care? What is the purpose of this curve intersection? Basically, this is pretty useful thing. This is pretty useful algorithm for constructing Gordon surfaces. You know, those surfaces that exactly interpolate the given network of curves. In order to construct a Gordon surface, what you will need to have the parameters of those intersection points on the original curves. So what we can do now is we can take those points and project them back to the original curves, and this way obtain the parameters. This is also pretty interesting exercise just to practice some, you know, basic operators with spline curves in OpenCascade. But before I proceed with projecting those vertices on the original curves, I need to understand which points exactly belong to the one or another curve. How do we do that? So basically here we can use the history of modification provided with the Boolean operation. For that, using this BOP, which is a tool that we passed explicitly to our function, we can extract the history. So there is such a thing as history. That would give me the handle of breptools history. This breptools history is a unified data structure provided by OpenCascade to store the history of modification throughout all modeling operators. So here we are going to take advantage of this history. It's simply a map. And basically what we are going to do is we are going to pass to this history our original curves and take out all the segments generated by the Boolean operation from our curve. Let's see how to do that. For that I'm going to iterate this list of arguments, and I'll use an iterator like TopoDS list of shape, then : iterator, args it, then args it more, then args it next. There is another syntax for the same thing. You can also use TopoDS list iterator of list of shape if you want. This would be essentially just the same iterator. Then out of this args it, I can take its value, like the current position of this iterator would give me the const reference to the current edge, representing my original curve. There we go. Now using this history I can access all the images of this edge after the Boolean operation has completed. This is done like modified, and you see it's going to give me this TopoDS list of shape, which is a list of images, which is quite fair because I really expect that from one edge I would obtain like a series of segments, not just one image. TopoDS list of shape. Images. Alrighty, so now those images are my curve segments. Now I'll use the same technique. So instead of having this compound here that was used to give me all the vertices, all the intersection points, I am going to collect a compound of vertices for all the images. So basically I declare another compound inside the loop. This BR builder I can reuse it, so I can move it out of this iteration scope, and then I'm going to iterate over the images. For each image I know, okay, it's an edge, so here instead of using this plain TopoDS shape, I'm going to downcast it right to my edge type. Here I have my segment, and now I want to take out all the vertices of my edge, so I'll use right now shape analysis edge. I'm using this tool simply because it has like some nice methods like first vertex and last vertex. So here I'm just going to use it like this in a little bit, you know, hackish way. because I do not really need an instance of this class, and I kind of use a temporary object and call its function right on the temporary object, just like if I was using like a static function. Here I can obtain the first vertex, then I can obtain also the last vertex. And now I can add those vertices to the compound object. You can notice that basically such an approach would bring me some duplicates, because the same vertex will be iterated twice, but I do not really care in this example. In some realistic code you would rather prefer to filter out duplication and check if you are not adding the same vertex more than once. Now I have this compound and I output it like this. You see that visually it's just the same result. It means that I have all my vertices as before, but now they are attached, they are associated with my original curves. Which is probably not visually evident, but according to this logic here, I have like those compounds for each current edge. So basically, in order to prove it works, I can probably just, exit from the first iteration. Like break the loop and see what's going to happen. You see that I have my vertices corresponding to the first curve in the list. Now, once I have this compound of vertices, I can go ahead and project those vertices back to the curve. For that, I'm going to use a tool. Its name is Shape Analysis Curve. Pretty similar in the name to Shape Analysis Edge, but here it's Shape Analysis Curve, identifying that basically I'm going to work with geometry and not with topology in my model. So let me go ahead and include this stuff first. The idea now is pretty simple. I want to take all the points and just project them back to the curve. For that, I'm going to iterate my compound. Here I'm going to use TopoDS iterator, simply because I know that in that case my vertices are the direct children of my compound. So basically I do not have to use TopExp Explorer that can do some nested iterations. So here they are direct children, so why not to use TopoDS iterator. Compound ID, then I pass here my compound. You see that here, unlike in TopExp Explorer, I do not have to specify the topology type. So I do not have to say I'm iterating for vertices, simply because I know the vertices are the direct children of my compound. There we go, and now I want to access the 3D coordinates of my vertex. In OpenCascade, topology is fully divorced from geometry, and that's why I cannot simply extract, I cannot simply call something like XYZ on a vertex. I have to use some specific tools. And basically to access geometry from topology, we use brep_tool. For vertex, we are going to use this pnt function. That's going to give us pnt as a 3D point. Now we can project this point to our curve, but for that we need to have the curve explicitly. Right now we only have an edge. So if we want to obtain a curve out of this edge, we first have to be sure that it's an edge. That's why I'm going to downcast it also here. So it's going to be the topological edge. And now once I have this edge, I can access its curve using the same brep_tool utility. But this time it's not pnt, it's curve. I passed there my current edge, and as a result this function will give me the parametric bounds of my edge and also the curve itself. So what I have to do is I have to declare these first and last parameters. These are the output parameters for this function, and then it's going to give me a geom curve. This curve is a B-spline curve, but here I do not care of its type, because I'm going to use a generic tool which is Shape Analysis Curve, and it can work equally well for splines and any other curve types in OpenCascade. So basically now I can use this sac.project. I'm going to project my point on a curve. Here I pass my curve, then point. Precision is probably just precision confusion. So if you do not know which precision to use, it's probably not the worst idea to start with this precision confusion. And then I'm supposed to pass there two placeholders for projection point and my parameter. So I need to declare my projection point and also parameter over the curve. And basically those parameters can then be stored in an array. So I'm going to declare a vector and just pass to this vector the next parameter I obtain from projection, or you can also call it point inversion operator. Because essentially this point already lies on the curve, it's by construction, and we only project it to the curve back in order to know its parameter. So let me put here just a continue instruction in order to be able to watch what's going on with this collection, how it's being populated. So I'm going to put a breakpoint right here, and let's see how it all works. Alrighty, so now what we have this list of parameters populated. You see that, okay, yes, I really have like two parameters identical next to each other simply because I use the same vertex twice. So what you can do about it, you can filter out all identical vertices beforehand, or you can also like just remove duplication from this list, which is probably not the best idea simply because, you know, the same projection will be duplicated, and you normally want to, you know, remove duplicated computations from your code in order to be more efficient. Then also this code does not ensure that basically those parameters are sorted. They happen to be sorted here just by lucky chance, but normally you would also need to go ahead and sort your parameters if you want them, you know, to be aligned with the parameter flow over your curve. And after that, you can use those parameters to, you know, do some other computations. For example, we are using those parameters to compute Gordon surfaces. That's it for today. Thank you for your attention and see you in the next episodes.